Hello everybody and welcome to another tutorial in our course machine learning, and in this video we're gonna see the application of linear regression that we saw in the previous videos. We already saw the application in Python, and today we're gonna see the application on R. So yeah, let's get directly to it. So first, to do some application, we're gonna need to download a library that's gonna contain the data that we're gonna use. So the library, like the command to download the library, is easily right here. Library MASS. There is many libraries, like pre-built libraries, and today we're gonna use this one. Later, maybe we're gonna use other libraries. So I'm gonna just copy paste so we gain time. So in this library, there is a set of data called Boston, and in order to actually visualize this data, we just can like type in fix Boston with capital B. Okay, so uh, this is the table provided with the data. You can see here we have roughly 506 rows and uh, 14 columns. That means 14 variables. So we're gonna see like which variables are related to which. So easily we can just say, actually I'm supposed to like follow this, but yeah, anyway, yeah, actually that's what I'm gonna do. Just plot Boston, copy. So here we're gonna plot all the available relationships, or like you can say uh, plots between all the kind of available variables. So these are our variables as a diagonal, and starting from this we can, for example, we want to know this, like what's the representation of this. This is between the variable this and the variable Knox. I'm not really sure what like what Knox and this stands for, but yeah, like I'm sure that it's like something meaningful because it's like real data. Now we are dealing with real world data. So yeah, so from these tables you can like predict which variables are actually meaningful to each other. For example, like when you see here, like these shapes, like the quadratic function shape, almost, you can know, oh, you can say like there is some kind of like a linear relationship or any kind of relationship between these two variables, while in some cases, for example, like here between I cannot really see well that ratio, something like that, I'm not sure about, and age. So you can see that there is no like apparent, like actually there is no relationship between them, these two. So yeah, so let's go to see other commands now, like to print the names of the available variables, just names Boston, as you can see here. So in R, it's really easy, like super easy to have the linear regression. And like in this time, last time in Python, I specifically showed you how to use the gradient descent, and now like doing this in R actually doesn't use any gradient descent. It uses the normal equation we learned in the previous videos. So it's like instant. Just you just type this command. By the way, the code is going to be provided with the tutorial, so don't worry about that. So you just type your command and boom, it's done already. So if you, oh sorry, I forgot the dot. Oh my god. Okay, so like instantly we just typed the command, we got the intercept, which is, if you remember, the W0 or B, which is bias, and this else dot is actually the variable we used in the command. So let's go back to the command to understand it well. Like, what did we do in this command? LM stands for linear model dot fit. It's just like a variable we name, but we say fit as a convention. So LM, as you see, it's like a function which stands for linear model again. Med v is our y. This is the y. Just remember it as the y. I'm gonna type it here just to. So the meaning of this, you can just imagine it that this is our y and this is our x. And then you type data equals, and then which data set we are going to use. That means you provide the y and the x. In which data set? We said here in Boston data set. So our y is medv and the x is lstat. Sorry if I'm pronouncing this like wrong, because like before I learn English, actually I learned French, so most of my pronunciation is actually with a French background, not English background. So sorry for that. Anyway, so we have the y and the x and the tilde here, and data equals Boston. So the representation of this is this exactly. And so the most important thing to remember here is LM, which stands for linear model, and the y, the x, and which data. Okay. So here, like as a result, you can see here, or you can like just type LM fit to have the result, or summary. I'm typing with one hand because my other hand is actually hurt, so sorry. Okay, the summary actually gives us more details. I told you that this is our bias and this is the the w1, or the variable that we're gonna multiply by the x. So we got them like the final result. This is the final, no gradient descent, no whatever. So you can see here the most important things I want to show you here is the here, like as I told you before, the bias, the W1 or W, the weight, as we learned before, the weight or the parameter, you can call it whatever you want. And one of the most important thing in R that you should know is the p-value. This is called the p-value. The p-value, like to know, is it's really helpful because it lets us know, is our variable really important in the model or not. So if this p-value is really close to zero, like really close to zero, that means it's really important. This side of the equation is really important to our linear model, or this variable, for example here else dot, is really important to our model. So you can see here it's 2 multiplied by 10 to the power of minus 16. That's really like almost like absolute zero, like really close from absolute zero. So you can say that it's really important. Both of them, the bias and the else dot variable, are both important for our linear model. Okay, great. Next, we already saw the summary. The the coefficient is also significantly Great. It's just like if you don't want to like see all this stuff and you just want to know how like how much is the bias and how much you just use this function and it gives you like only the result that you want to see. This is the confidence interval. What does it mean? It means the like how much we are confident of our results, like how much our results are really like we can depend on these results. So you can see here that it's like 97.5%. Like you can know that this is like the most important result like you can focus on. So this is the for the bias and this is for the as a coefficient, but usually you just take these. So this is just like to know more details, but as a beginner you just need these like the ones that appears here, or just use the this function that gives you directly the values that you need. Next, so now we're gonna do like the most important thing, which is predicting a given like new given data, because before we had like uh by the way, I didn't plot the let's plot so I can show you. Oh my god, my hand is, I'm using only one hand as I told you before, so that's why actually I'm copy pasting, because it's much faster for you and for me. Okay, this is the data we are like we fit our model on. So this is the L stat we saw before and the med v. So this is the L stat as x's and med v is our y's. As I told you here, y, x. So like you can guess that our hypothesis function, if you remember, it's gonna be almost like this, like this. So let's draw our hypothesis function that we just like built, which is lm dot fit. Lm dot fit is our hypothesis function. So how to draw that? Oh, sorry. So how to draw our hypothesis function? You simply copy paste this. Upline, remember this function, upline. This is here you put the model, like what you named the model. This is line width, because this is like a linear function, so we have a line. So line width equals 3, and you also can add other parameters. For example, if you want the color to be red, you just maybe, I'm not sure, but I think red is number 2. Yes, I was right. So you see, this is our hypothesis function that we deducted. So if you, for example, say 5, which is here almost, 5, give us like 30, 29, I'm not sure, 30, 20, like almost 30. So 5 should give us like 30. So let's see, let's predict. And to predict new like values that we're gonna give to our model, simply predict function. So here is the function predict, give it the model, give it which like data, because like it's called frame of data, because you're gonna give it like a kind of frame. You can imagine it as like a portion of data. So we're gonna give it like, you can give it as much x as you want, like L stat when L stat equals 5 and L stat equals 10 and when L stat equals 15. Interval equals confidence. This is totally optional, but we're gonna do it anyway. Like it's good to see all. options available. So yeah, okay, confidence, like interval equal confidence. You remember the confidence interval we had before? That means like the predictions we're gonna have are going to be like in the minimum value of the confidence interval, because it's like the interval now is like from the lowest to the highest. That means from 33.44 point like blah 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 to 35.65 blah 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 blah, and -1 to -0.87 blah blah blah. So this is like two intervals. One represents the bias, one represents the W or the weight. You can call it whatever you want. And here, like the predictions are based on three values: the lowest value, the median, or like the value in the middle, and the highest value. But you can like since you are beginner, and I don't think you're gonna need that so much, so you can just get rid of this and just use predict, and it's gonna give you like the medium, the closest value for the model. So yeah, so here is like the three values. It's for 5, 10, and 15. So for 5 we have 29.8. I was right. Here I said it's almost 30, so I was right. Now here it's 10, 10, so 25, 10, you can see it's 25, and here 15, 15, so you can see it's 20, 20 something. So you can see, so remember well this function. I like to like give you the understanding behind the functions, not like the syntax of the function, because I'm gonna provide you also with the code. And the most important thing is to understand what exactly does happen behind these functions, like what do they actually do, not how to write them. So yeah, as I said before, you give it the model we learned, then data dot frame. This is like a whole new function. It means like we gonna give you a frame of data, then you provide the values for the variable else dot equals. See, if you remember the first video we studied R together, we like defined a vector like this. So 5, 10, 15, and then this is like totally optional, but you can use it if you want to. And then, so we already plotted this one, we already did this one. So yeah, so we plotted our data, and it's real world data, it's not fake data. And we predicted our hypothesis function. uh, we did a bunch of other stuff. I told you also about the p-value, which is really important to understand if the variable is important to our model. So now we saw all of this, but we did it only with one variable, like one x. What if, like, usually in real world we don't want to use just one x, we want to use like multiple x's. How can we do that? So you just do the same as we did before, and we're like given the other x's, you just plus age, for because last time we did it like that. Last time it was like that, and now it's plus age. That means age is our new x, or x2 if you want to call it like that, x2. So we have our new model. How, yeah, okay, let's plot it first, or yeah, let's see the summary first, and then So here you see that we have also a new variable which is age. Then you see the p-value. The p-value for age is kind of higher, way higher than the other variables. So you can say that age is not that much significantly important for our model. So from here, as I told you before, we already detected that age is not that important for our model. And sometimes some variables are actually bad for the model, so be careful. Like you can try all the variables. By the way, if you want, for example, to use all the variable, all the x's, I remember when we used names and we got all the available variables in Boston dataset. Where? Yeah, here. You see, like we have all these variables. What if you want to use them all? You cannot just like write like here fit, yeah, fit, and then like plus age plus blah plus blah and like multiple times. So the solution is to directly put the dot. What does the dot means? It means all other variables than meddv. And that's how. Now let's see the summary. So let's see the p-values. So here it's really small because it's multiplied by 10 to the power of minus 12. It's important. That's the bias. Intercept is a bias. Just put it in your mind. Intercept bias. This is small, but not that small. This is way more smaller, so it's more important than the one before. This is too high. This is totally like we should like get rid of that. This is small, yeah, but not that much. This is really small, so we're gonna use that. Also, this is very good. This is bad. This is bad. Age is bad. Is not that good. This is good. This is good. Not that good. Good. Not that good. And good. So you see, from the p-value, I could determine which variables that are important for my model and which variables that I don't actually need and actually I should get rid of. So remember, after you fit your data, use the summary and watch out for the p-value. Now, yeah, you remember also when I told you about the quadratic function. For example, when we go back to the plot of our data here, you see that yes, we had like a good linear model to model our problem, but you see it's not actually like a line, like really line, like it was quadratic. It's like that. It goes like that. So it's quadratic. So definitely you're gonna think, oh, quadratic function is better. So simply you can fit your data using quadratic function using this I. Uh, so like create new model, this fit2 linear model. You can use a quadratic function with the same function lm, which stands for linear model. This is our y, this is our x, plus x squared, the same x squared. You're gonna say, but why didn't we just say like that? It's because um, this symbol is like have a lot of meanings in R, so you need to use this function I because of this symbol. So that means square, and so it doesn't make problems for understanding for the compiler, and that's all. So we can copy that and define our new model, which is quadratic function, because this is square, so x plus x square. So you can see it's a quadratic function, and see the summary. So now you can see that our x square has a really small p-value. That means it's really important. That means we can deduct from here, comparing to our previous normal linear model, so with just x without any, of course, I'm not talking about this, I'm talking about the first time when we used the x. So you can see that this is like much better model. This is much better model. Like so we can deduct that the quadratic model is much better than the linear model in this example. So how to make make sure of that, like add certainty for our deduction. There is this special function called ANOVA. This function ANOVA actually takes as parameters two models and compare between them and see which one is better for your data. So you can see here, so model one. Oh, by the way, the model one is using all the other variables. Let me, because it's not fair to use all the other variables for one model. And okay, again, now it's right. So yeah, you can see here like the p-value in the second model. The second model, that's model one. By the way, I'm not sure. Let me see if I want to make this. I just hope that you can see that. Okay, so I'm not sure how to make this bigger, the screen bigger. I'm gonna look for it later, but I really hope that you can see that. Anyway, so model one is our linear model without any, it's not quadratic function, and the second model is a quadratic function. So you can see here that the p-value is really small for the second model. Directly we can say that the second model is the best, and also the f value is better to be higher. So, but I think the most important is the p-value. So the p-value is small, that means it's the best. So this model is way better for our data. Now finally I want to predict using the first model, like predict for the same data we saw before, for the first model and for the second model, and we compare. Okay, so this is for the first model, the non-linear model. You see here like 29, like when it's 5. Let's plot the data. Okay, here's the data. So for 5 we had like 29.8, like we saw already that before. And then here for 5 we have 32. So let's check if it's actually better. For 5, 32 is almost like here, so it's better. Like you can notice that it's better. Let's see some easier one, like for 10. For 10, 25 here. 25 is here. And for 10, 23 is here. So you can see that the quadratic model is actually like more centered, like it goes in exactly in the center of the data like that. While the linear model is just like line like that, it doesn't care where is the center, or because it takes all the data as a repair. I'm not sure that English word is French word for sure. So it takes that model to draw the line, the hypothesis function we had before. So that was linear regression for one variable and multiple variables, as I showed you in R. And thank you very much for watching. I'm gonna see you next video. And as I said before, the code is gonna be provided also. So I hope you enjoyed it. Thank you very much, and see you next video.